firmware at Leonardo is analogous to FPGA. So I'm going to be telling you a little bit about FPGA security in high assurance environments. All right, so a bit of an introduction to Leonardo, if you're not aware. You might not know if you're not in the industry. International Industrial Group, the main global companies in aerospace, defence and security, and one of the UK's leading aerospace companies and biggest suppliers to the UK MOD. We have 9 main sites across the UK. I'm based up in Edinburgh. That's our radars and advanced targeting line of business. My role there, I'm based in the product security team, so I work on implementing security functionality in FPGAs for aerospace applications. A bit more information about UK presence. So Edinburgh works quite closely with Newcastle, and particularly me with the product security team based there. We also have our electronic warfare line of business in Luton, Lincoln, ISP down in Basildon and Southampton, that's integrated sensors and protection. We have our helicopters division in Yeovil, and cybersecurity division is based in Bristol. We also have a significant international presence, so our 4 main domestic markets are the UK, Italy, Poland and the US, but are based all over the world. I also take this opportunity for a shameless plug for our vacancies, because we're also hiring at the moment for security-related FPGA engineers. So if you find this interesting and you want to work on high assurance, high-grade crypto, let me know, speak to me, send me an email. So high assurance, what does it mean? Here's a definition. So having a very high level of justified confidence backed by rigorous evidence that a system will behave exactly as intended, even under adverse conditions. So commonly in application, what that means is you see that applied to safety or security. So they have quite a lot in common, safety and security. Systems should behave as intended and be protected against failures. Both of them use controlled processes. You have to provide a lot of evidence, you have to do a lot of verification. And they both use risk-driven processes, or risk framework, to identify what mitigations need to be put in place. Important differences though: safety is against accidental failures and security is against intentional threats. There's also a difference here in the failure modes for these. So for security, if something goes wrong, you probably want to stop pretty quickly. And for safety, you probably don't want to stop pretty quickly, but you want to fail safely, which looks a little bit different. So quickly touching on safety before I move on to security, because it is quite similar. If you work in the aerospace industry, you'll be familiar with DO254, which is the design assurance guidance for airborne electronic hardware. Basically, the higher your design assurance level, the lower the failure rate of your system. So to get to that higher level, the sort of things you'll be employing is sort of at the highest level, maybe like redundancy. You might have different teams working to the same set of requirements to verify against each other and implement redundant solutions. You're going to have traceability and very granular requirements right through from system level to your FPGA requirements and into your lines of code as well. So yeah, much more verification for higher assurance. Appliance security, again, this is against intentional and malicious attacks instead. So there's a number of standards associated with that. You might be looking at the risk assessment frameworks, some of those listed there. And the previous talk did a really good job of the attack paths, so the sort of activities involved in these. Risk modeling, so these are sort of databases of adversarial tactics and techniques. Attack is a more general one. Embed is specific to embedded devices. And Atlas is a newer one, and that's for AI-enabled systems as well, and specifically for attacks against those. We follow Secure by Design quite closely. This isn't specific to the MOD, it's whole of government, but MOD is one of the most prominent users of this, and you can Google that and look it up if you want to. And the sort of methods and practices employed here, at the end of the day, it's about building a layered approach, and it's about having that verification in place, so you don't have single points of failure and it works as it's supposed to. Here are the guiding principles. I'm not going to go through them all, but the main thing I want to call out is that actually a lot of this is process and planning. Actually implementing the stuff and architecting the solution is principle 4. And the rest of it is about managing the risks and having that framework in place and the process in place to do security properly. Also, the last principle, It's quite important. So you need to be able to update your risk assessments and frameworks over time as threats evolve as well, and make sure that the sort of ongoing assurance requirements are met. And that brings me quite nicely onto my next slide. FPGAs are quite good at this through life stuff because you can't update them, obviously. So FPGAs are quite good for high assurance security because, of course, you have less components involved in a software-based solution. Software stack has many different components. And with an FPGA, at the end of it, you get fully deterministic design that can be certified and audited. You can get strong configurable isolation at the hardware level as well, and physical partitioning, and that's making use of the tools like isolation design flow in Vivado. FPGAs are also well suited to implementing cryptographic algorithms, so things like AES and SHA-3 are designed with hardware in mind. Also quite good for root of trust applications, particularly flash-based FPGAs, because you don't have to load your bitstream externally. And of course, you have the crypto agility and providing updates over time to your FPGA too. They're also really good for safety stuff. So it's really good for an application like aerospace where you're concerned with both potentially. So the first thing is to get the basics right. So sort of the baseline. So turn on the passive features, and the reason I say consider using the active features is that they do need to be used in a layered approach. So, for example, if you had access to a TRNG like the one in the Athena core in the Microchip devices, maybe don't only rely on that for your random numbers in a high assurance solution. You might want to use it to augment random numbers from your own TRNG that you've implemented in the programmable logic. So you can use a ring oscillator for that. You can use PLL-based TRNGs for that, for example. A lot of other things listed there. Some of the more interesting ones, external DRAM memory encryption. So this is something with the latest Xilinx devices. It has AES XTS that can actually inline encrypt stuff going to DRAM, which is quite interesting. But don't only rely on it. So, there's lots of certifications associated with vendor devices. But it's also important to know what these actually mean as well. So common criteria, for example, you have your evaluation assurance level 1 to 7, I think. And what this does is it provides that assurance that the security is doing what the vendor says it's doing, but it's not necessarily how secure the device is. For example, it might have a pretty high assurance level, but it might not have that post-quantum crypto that you need for your future projects. And at the end of the day, as I say, you can't only rely on the vendor stuff. You have to implement a layered approach. So this is where implementing your own crypto, for example, is needed. Here's an example of when it's not sufficient. So the previous talk also covered this. So I'm sure you're all experts now, but a little refresher. This is the Starbleed attack because it uses the WB star register and exploits the malleability of a CBC. You can see how that works. The ciphertext is XORed directly with the plaintext. So if you modify the ciphertext, you're directly manipulating the underlying plaintext too. And by doing so, the authors found a way to manipulate the configuration engine and redirect the decrypted ciphertext into this WB star register. When the authentication check fails, it stops the boot process, but you can subsequently read out the decrypted plaintext in an iterative fashion to retrieve the whole bitstream. The HMAC key is also stored within the encrypted bitstream, so you can also retrieve that. And this is the response from Xilinx. So you can see at the bottom where I've highlighted their stance, saying the complexity is similar to well-known DPA attacks, differential power analysis attacks. So therefore, it doesn't weaken the security posture of the device. It's debatable, maybe. It depends on your risk profile and where your threats are coming from. So in a high assurance product, that would be acceptable, and that's why you build in the layers of security to protect against that. So building that layered solution and some examples then. So a good starting point is probably the secure boot root trust stuff. So your keys are probably derived somewhere or loaded in the secure boot process if you're using an FPGA. So you can use a layered approach to that. Perhaps part of your key is an SNVM. Maybe you derive it using a puff, for example, to get your whole key. Maybe you load it from different areas. For any bitstream loading or any configuration data that you're loading that's security involved, you probably want to check the integrity, the authenticity, and the confidentiality of that. Secure boot process, you might want to consider additional protections from glitching or fault injection as well, because this is kind of the root of trust. If someone's able to get past this, then the rest of your security functions are kind of not very useful. Recent example of that, last month, the Bliss attack on the original Xbox One. Using 2 well-timed voltage glitches, you can get past the boot ROM for the Xbox One. I think Microsoft actually put in glitch detection circuits for this, but they weren't available for delivery of those first batch of consoles. So that's why it only works on the very original ones. It did also take them 12 years to find this exploit, so they've done a pretty good job anyway. Lifecycle management, so make sure you know a way to how you're going to rotate your keys, how you're going to have that cryptographic agility, and lock down your configuration methods. So locking down the configuration interface and any test ports, that's a good thing to do, or just remove it entirely. So for example, you might want to use an anti-fuse FPGA that can only be programmed once, although granted that's maybe not so good for the crypto agility. So in that case, you use a flash-based FPGA where you don't need to load an external bitstream, or if you really need the resources that an SRAM-based FPGA has, get creative. So you could layer that with some additional physical protections, for example, or I think you can buy decapped FPGAs from Xilinx and maybe you put your own NVM in and package it up yourself. Or use a layered approach. Maybe you want to use anti-fuse FPGA to check the bitstream for your SRAM-based FPGA and program that up. No one said that high assurance was cheap. And use the right crypto as well. So this is NCSC's sort of post-quantum timelines. 2028 is in a year and a half. So you're going to want to start thinking about the standards that have come out. There's some on the left there. And FNDSA is an upcoming one. FFT over N-true based lattice digital signature algorithm. And that has floating point numbers in it. So that could be an interesting one for FPGA engineers to implement. And the standardization of this is ongoing as well, so expect more standards to be released as it goes. And then after your secure boot, you're going to want to consider runtime as well. So, an active anti-tamper detection method might be one way to do this. This picture at the bottom is from the impedance verif paper that was presented at CHES a few years ago, the Cryptographic Hardware and Embedded System Conference. Use a ring oscillator-based network analyzer to measure the impedance profile of the PDN, power distribution network of your FPGA. And that, depending on how it's configured, makes a sort of unique profile. Using statistical analysis, you can then check when that's modified or tampered with. So for example, if someone removed the decoupling capacitor to support a power attack, you'd be able to detect that. Or if someone put an EM probe next to your FPGA, you'd be able to detect that. System monitoring vendor IP as well. The likes of SecMon IP from Xilinx you can use for post-boot protections. And yeah, maybe use some physical protections as part of your high assurance layers as well. And authenticated encryption should be used for any sensitive data in transit and also at rest. Consider side channel protections as well. So there are people out there whose job it is to break your implementations, and I know because I've met them. The SCA protections from the vendors and your SCA protections will always have their limits. So vendor details, on how many traces, for example, it protects up against aren't publicly available. Occasionally, through NDAs, they are. And if you're implementing your own crypto, basically depending on your risk profile, that'll tell you what sort of things you need to implement for side channel protections. And that could be constant time execution at the most basic. Maybe there's some masking involved as well. So this is the physical isolation stuff, like in relation to single chip crypto. So what is single chip crypto? It's basically where you can have red and black data on the same device. Red data being the sensitive data. And this lowers complexity by, for example, removing the need for a separate FPGA to separate your data out. And in doing so, separating them out, you're reducing that leakage path between red and black data, which provides a stronger assurance statement for any certification you're going through. On the right-hand side is an example of how it works in Vivado. The tool is also available for Microchip and Intel devices with the names in the bottom left here. The important thing is that you consider it at the start of a project because it involves a lot of floor planning, for example. This is going to impact your routing inside the device and also physical pin location. You can't have red and black pins put together to maintain that isolation. Here's an example of how it works in the application. So you can see in the placed and routed design there that maintains the physical separation. An emerging trend, something I wanted to touch on as well. So this is quite big in academia at the moment, and of course it takes a while to come through to industry because we need to wait for the standards to come out. But privacy enhancing cryptography is an emerging area, and it opens up quite a lot of new techniques and opportunities for crypto that we've not seen before. Some of the primitives involve zero knowledge proofs, secure multi-party communication, fully homomorphic encryption, and there's a standard due in 2028 for that. Hardware acceleration for these is going to be vital. State of the art at the moment is about 10,000 times slower than other methods. Actually, a lot of the academic stuff on this is focused on ASIC so far, so I think there's a big opportunity there for FPGAs and us to get involved here. Here's an example of an application, P1735. If anyone's not familiar, it's a method of encrypting IP to be used with vendor tools so that, in theory, a user can't see the source code. The problem is that the people using this, the IP vendors, the designer, the tool vendors, are mutually distrustful of each other, and it inherently involves some trust because you're relying on the vendor's private key that's embedded in their software to decrypt any IP. Garbled circuit protocol is a PEC primitive. It basically allows two parties to jointly evaluate a function without revealing what their inputs are to each other. And the result of that is that there's no embedded private keys needed, and you get that zero trust model provable security. Another example, Election Guard. So this is by Microsoft. This was developed. It uses homomorphic encryption, and homomorphic encryption basically allows you to perform operations on that encrypted data without decrypting it first. So that really removes a big chunk of your attack surface. Zero knowledge proofs, another primitive it uses, and you can prove that all of the votes are valid and correct without actually revealing what the votes are. So the result of that is the end-to-end verifiable elections without revealing how anyone actually voted. And that's about it. Takeaways, so start with the vendor feature, make sure you turn them on, but it probably involves more than that. And you need to build the layers based on your risk framework that you've developed. FPGAs are a pretty strong foundation for them if they're used correctly, and secure boot and runtime protections are going to be crucial there. It's not a box ticking exercise. You have to use the evidence-driven, risk-driven approach to this. And that's it. Thanks very much. Any questions?
Go back one slide for me. The last one, Very much where I started.
Yes.
That's what CRA is asking for. It's bringing that high assurance environment into every day because we can't escape the security problem now. Okay, that's the challenge that we've got. Now, okay, it doesn't need to be quite as high for a consumer product, but not many FPGAs go into consumer products. That's the delta on that one. Yeah. But let's face it, if we're making it for an industrial control system or something of some level of assurance, discipline is not radically different now.
Yeah, yeah. Well, it's you know, for the secure by design, for example, that can be something that's applied to every product. It's not just high assurance. So
exactly.
It should be.
It should be there, and it's the discipline side of it, the discipline, the evidence driven, and that's the key thing. Where historically we've got away with a lot as engineers, a lot when you actually consider it. Peter has a question.
I haven't looked at the tech in particular, but I'm making the assumption that what you're doing with that is, with that IP that you're putting into the FPGA, you're providing an extra key that scrambles the logic that then gets enabled in runtime, and then obviously it works as it says on the tin in terms of IP. Yes?
Yeah, essentially. Yeah.
Right. Okay. So that's something that we do. But anyway, the question that I have then is, have you looked at that? I make the assumption that the key becomes something that's stored somewhere, and then you have a spider's nest that goes through the FPGA to where it's going to be used. How does that impact doing design separation?
So this is specifically for P1735.
Yeah.
Key.
If you're having a key that's scrambling the logic.
Yeah. So essentially how it works, and I suppose the vendors, tool people will be the experts on this, but the private key that they embed within their software essentially decrypts it at runtime, so it can be used for synthesis and place en route. So when it comes to the design separation methodology, actually when it gets to that point, the IP is already decrypted. So it doesn't have an impact on implementing isolated designs. It's purely encrypted before it reaches the tool, and when the tool needs to use it for something.
Okay, so it's not the same thing. Okay, right, okay. Because what I was describing, I think with design separation, it's mutually exclusive. You can't have both unless you're restricting it within the device itself.
My understanding is it decrypts it before it uses it for any sort of design separation.
Right, okay.
Thank you. So you're talking about assurance here. How important in your verification are orthogonal tools? And I'm thinking especially about design separation. Is it important for you to have some sort of additional validation that the tool has done what it's told you it's done? Like, for example, in avoiding these long wires.
Yeah, so that's part of the tool. So I think all of the tools that I mentioned in the slides have an accompanying tool that kind of verifies that and runs a load of design rule checks associated with that. So in Vivado, it's the Vivado isolation verifier, and it's the Microchip separation verification tool, for example, in Microchip. So they're all used to that end to give you that assurance that it's the tool is doing the correct things, that it is separated appropriately according to that verification methodology, the isolation methodology. After that, obviously when it gets put onto the device, there's maybe an in-between there, and that's when you might need to look at the design specifically. Someone might be auditing that as part of your assurance process, for example. So at the gate level.
And I guess that kind of is pretty similar to the verification paradigm where you want separate people or separate systems to validate and not reuse incorrect ideas.
Yeah, no, absolutely. Yeah, that's the key point. I mean, it's the verification effort is much greater for this. So, yeah.
Thanks.
Okay.
Can I just qualify what you just asked? So you were talking about the MSVT from us in terms of doing the validation of the separation flow, right? And you say, do you need an independent tool to actually validate that what that is telling you is correct, right? For us, you don't. We're in the UK. That was developed and evaluated by GCHQ. So they have gone through it and made sure that it does what it says on the tin. So you've got that level of assurance because you're in the UK. Okay.
Check. No. Right, okay, no, we're good.
Thank you.
Okay. All right, so we're going to take a break now until, let me check because I can't remember the timings. 1:30. There you go. Right, and then we've got 2 after 2. So lunch is served in there where the coffees are. It'll need to be extracted from the boxes because they're still there as we start. But we'll see you back in 50 minutes. That's okay. Thank you.